So what I'm going to do in this one is a two-element assembly, but I'm going to do it by direct sum of forces at each node. So this is the one I start off with, but I think this go around in class we started with the some of the element forces actually, but this way is probably the most rigorous, I guess. It's the most obvious where it comes from. After you go through it, there really is no doubt about its validity, I guess, right? So I'm going to just start with this simple two-element problem. Each element has a different spring stiffness, okay? The boundary conditions actually are going to be relevant. I got a force on the right-hand side, and it's fixed at the left-hand side, but it really doesn't matter because we're just going to be assembling the stiffness matrix, okay? I wonder if I do this, will it get so... Let's stay the way it is. Oh, that's cool. It doesn't screw up the focus. Okay, so what do we have? Okay, we got node 1, and then a spring connecting to node 2, and then the second spring connecting to node 3. So we have node 1, node 2, and node 3. This has a spring stiffness K1, excuse me, and a spring stiffness of K2. All right, so we know from before, whichever video you looked at, it actually doesn't matter, that when we assemble this, we are going to get the following answer, right? We are going to get a global stiffness matrix that is going to be a 3x3, okay? Relating the displacements D1, D2, and D3 to the external forces F1, F2, and F3, right? Oops, excuse me. And this is going to have the following form. K1 minus K1, 0 minus K1, K1 plus K2 minus K2, 0 minus K2, and then K2. So that's the result we got when we did either element force superposition, with the augmented stiffness matrix, or, sort of the direct approach, which we'll do at the end, all right? So this is the answer we should get, and we'll show how it comes about from here. So what we're going to do instead is we are going to do sum of forces on each node, okay? So let's start with node 1. So the free body diagram is going to look as follows. Here's node 1. If there's an external applied force, F1 on the system, it's going to go to the right in the positive x direction. And then we have also acting on here the force due to the spring being stretched, right? And so that's going to be K1 D2 minus D1, excuse me. And so you can check the sense on this. This is such that if it's in tension, if D1 is greater, if D2 is greater than D1, this quantity is positive, and it's in tension, and the force is to the right, okay? So obviously when we look at this and we do sum of forces, we have F1 plus K1 D2 minus D1 equals 0, or putting it in the standard form, we have K1 D1 minus K1 D2 equals F1. All right? All right. Now, here you can see already that is our first discrete finite element equation, and that matches up with what we get here for the first row, right? K1 times D1 minus K1 times D2 plus 0 times D3 equals F1, all right? So that one works out. Now, likewise, we can do sum of forces on the second node. Now, here's the second node. I'm going to put the external force here, F2. If there's an external, well, if there's an external force applied at node 2, it's going to the right in the positive x direction. We have, all right, the force from the first spring. Again, if it's in tension, it's going to act to the left. So this is going to be K1 D2 minus D1. And we also have acting to the right the spring force due to the second spring. Okay? And that's got a spring constant K2. And we drew it in tension. And if it's in tension, then D3 has to be greater. Oops, I keep saying one thing and writing the other. D3 minus D2, or the fact that D3 being greater than D2 puts it into tension. All right? Okay. Now we can rewrite this, and you can do the math yourself, but what you can see here is we get, well, let me do it. I'll do the steps out on this one, okay? So going to left, we get minus K1 D2 minus D1. Then going to the right, we get plus K2 D3 minus D2 plus F2 equals 0, right? And now if we combine terms, we'll put multiply by -1 and bring the F2 to the right-hand side. Okay? And the terms multiplying by D1 is going to be a positive, positive K1 D1. It's this term. Multiplying by D2, we have a combination of both K1 and K2. All right? And it's going to be, right, we got to, remember we multiply by -1, so we have a positive and a positive. So it's plus K1 plus K2 times D2. And then finally, what am I doing? Sorry, on the first term, it's positive for D1, but we multiply by -1, so there's a minus out there. Now for D3, again, it's positive, but remember we're multiplying by -1, so we get a minus K2 D3. All right? So you can check that this is correct. This is correct as well. You can check that by doing the algebra. Okay? Again, that matches the second finite element equation we get here. Minus K1 times D1, that's the first term, plus K1 plus K2 times D2, that's the second term, and then finally a minus K2 times D3. And how am I writing? Okay, and that's what we have here, and that all equals F2. All right, and finally we do sum of forces on the third node. All right, so here's the third node. If there's an external applied force here, it's going to be F3, and if it's in tension, the second element will exert a force to the left of K2 D3 minus D2, correct? And so that gives me minus K2 D3 minus D2 plus F3 equals 0. And now rearranging that, multiply it by -1 and bring F3 onto the right-hand side. And then we get a minus K2 times D2 plus K2 times D3. All right? And again, That's the third discrete finite element equation, and that matches what we got previously. All right? So sum of forces works. I think it's probably easy for anyone to do. Actually, I don't even need to derive the element stiffness matrices to do this. Obviously, this will get more complicated as we add more elements, and definitely as we add more complicated elements, this is not going to be possible, or be very, very difficult. So this practically is not what we do, okay? Practically what we do is actually the direct method that I'll show in the third video, okay? But this is a good way, like I said at the beginning of the video, usually I do this as the first approach to show what the discrete finite element equations are. There's really no arguing with sum of forces. I mean, we all learned this back in statics, right? So that is what it is, all right? So I hope that's helpful.